Bismillahirrahmanirrahim. Good evening. Today we'll try to do a simple summarize to this article. The article's name today is Crystalline Size and Strain Analysis of Nanocrystalline to Lanthanum Selenium Manganese Oxide Peroviskite. And here we have doping rate X here equal 0.3 by using the Wilson whole plot method. At first, we will give simple definition to Wilson whole plot method, and we will explain something by using the periodic table. We will give simple definition to double exchange. Let me use the slideshow and start. Here, the doping rate equal 0.3. We will explain something by use the periodic table to illustrate lanthanum belong to alkaline earth, cerium belong to alkaline earth, manganese it's a metallic element, and we will explain the structure size effect of the mixed valence perovskite manganese, what the structure size will do on the perovskite manganese, explain the double exchange interaction. Actually, I explained the double exchange interaction in the perovskite lecture, but we will do a simple review to it. The particle size effect on the ferromagnetic properties. We will use some graph, some plot to explain, to review the ferromagnetic area, the paramagnetic area, and the Q temperature. The temperature point will be between these two areas. We'll explain what is the tolerance factor, why is it important element, the sol gel, the chemical process, and like I said before, Wilson whole plot method and Bragg's specs. Now let's go directly to start in our lecture by start with the periodic table. Like I said before, here we have lanthanum. Lanthanum and cerium belong to alkaline earth. Manganese belong to metallic group element. Here the doping rate is 0.3. By that will be 1 minus 0.3 to be like that 0.7. We have condition like explained before. The total to these two numbers must be 1. Now let's talk about the size of structure of mixed valence perovskite manganese. Here is important. Why? When we do some change in the size of structure to this perovskite manganese, what we'll do? Why is very important? It's very important because when we do change in the structure of mixed valence perovskite manganese, the structure will change and the physical properties. Actually, the physical properties is the most important thing to us. That means when change to more or less, to be more or less this size of perovskite manganese, the physical properties will change. Now, let me explain this note. We have strongly dependent on physical properties, sure, with crystallite and, or we can say, particle size of the system. By that, when particle size change, the physical properties will change because there's strong relation between them. The mixed valence to lanthanum, cerium, manganese, O3 perovskite manganese show important thing in the ferromagnetic area, show closal magnetic resistance, where in the second half from this plot after the Q temperature. That means here the magnetic properties is started after skip this Q temperature. along with ferromagnetic ordering, like I explained before. Now, the phenomena, now we will do simple review to double exchange. Why? Because the phenomena of closal magnetic resistance is explained by double exchange interaction. By using the double exchange interaction theory, we can explain the closal magnetic resistance in the ferromagnetic area between these two different charge of manganese, 3 plus, 4 plus. Here, this plot explains to us how the electron can jump from level to another or from area to area by using the oxygen like the bridge. Let me explain that by using other words. Here, at first, why we have here 3 plus, not 4 plus, because the manganite can be full by using 7 electrons. Here we have 4 electrons. What that mean? That mean I have 3 holes, 3 plus. The holes charge is plus, like we know. And the properties of double exchange interaction, the spin will jump from this EG level to the oxygen bridge, but the spin direction will be the same. And after that, jump again from this oxygen bridge to the next EG level, belong to manganese 4 plus with the same spin direction. That means the spin direction will not change ever. Like I said, will be something like that. Manganite here, it's full by, and the other has opportunity to accept another electron. By that, the electron can jump from here to here, and after that, jump to another place and keep going. This, the double exchange interaction, simple review to double exchange interaction. Now, let's say when the particle size decrease, the ferromagnetic will increase or decrease. Actually, the ferromagnetic properties will decrease by decreasing the particle size. Why? Because by decreasing the particle size, the size effect be finite. And the double exchange, by that, the double exchange interaction will decrease or will be weaker. That's mean by decrease the particle size, the size effect will decrease, and the double exchange interaction will decrease. The structure phase transitions in perovskite, the general formula to perovskite, like we know, AbO3, AB are the cations, and 3 atoms of oxygen, can be identified by structure tolerance factor. The structure phase transition in perovskite can be identified by tolerance factor. Tolerance factor is important element here. It's used to determine the stability of perovskite oxide phase for given set of anions and cations, It's important to determine the stability of perovskite oxide phase for given sets and ions and cations. Tolerance factor, like I said, is an important element, and perovskite cell parameter is two important elements related to the symmetry of perovskites. That means tolerance factor and perovskite cell parameter can make the shape, the structure of perovskite be symmetry. Yes, we can say symmetry. It's meaningful word. that significantly affect the dielectric properties. Significantly affect, a huge effect we have on the dielectric properties. The perovskite structure is stable. I take this information from this article. Below when T bigger from 0.89 and smaller than 1.02. Here, the catalyte size also affects on the lattice strain in nano samples and on the properties of nanocrystalline manganites. Here, the function of tolerance, it's not very important image to me because not strong related with my topic about the doping, centering temperature, but the important information in the next slides. They studied the authors here, the scientists here in this article, studied the size-dependent structure. This related with my topic. The size-dependent structure behavior of nanocrystalline. The size-dependent structure behavior of nanocrystalline to lanthanum, selenium, manganese oxide, O3, peroviskite manganites, synthesized by into composition the sol gel method. We will use here some important about the change in the size-dependent structure. And they use the sol gel. It's a chemical process to produce pure perovskite oxide. Has some advantage about low cost and consume temperature less than other processes. Here, let's talk about Williamson whole plot method has been used to what? To estimate, and at the same time, it's we can say it's a simple definition to Williamson whole plot method. Estimated is used to estimate the crystallite size and lattice strain. Is used to estimate all of the lattice strain and crystalline size by peak width as a function of 2 theta. They used various here, it's important. We have a different amount of temperature, started from 900, finished with 1300 Kelvin. To get what? To get pure polycrystalline, lanthanum, selenium, manganese, O3, with different crystallite size. It's a huge similarity with my topic in my seminar or what I will do in the lab. I will use different high amount of temperature, you can see the centering temperature, and different crystalline sizes. Let's come back to our slides here. The scientists used to X-ray diffraction patterns to analyze the crystal structure. Here we have 3 methods: sol gel, Williamson whole plot method, like I said, to estimate the crystalline size and lattice strain at the last different amount of temperature, like strain temperature. We'll explain some another important information on it in the next slides. We use it to multiply the nanoparticle to these atoms. I will explain that by use a clear image to prove these few words. At the last, they used X-ray diffraction patterns to analyze the crystal structure. Now, like I said, different amount of temperature started from 900 Celsius. Sorry, not Kelvin, Celsius. I have a mistake here. It's It's not a Kelvin, it's Celsius. It's a huge difference. 900 Celsius, Allahu Akbar, Allah. Started from 900 Celsius, finished at 1300. What here we have at this plot, X-ray diffraction. Here we have five colors. The last one is at high temperature, 1300. Here we don't have any impurity, zero impurity. That's mean high pure peroviskite we have, but at the last four level, started from 900, finished with 100 to 1200. We have impurity, but it's very small, approximately 200%. Here in the X-ray diffraction pattern, no secondary impurity phase, like I said before. And at the last four levels, we have 100, 200%. Now let's talk about these three different colors, red, green, blue. Here at X-ray diffraction pattern of this structure, calcinide at 1300 Celsius, calcinide, and the atoms be bigger than, and we will talk about that, maybe started from 140 and be bigger to be equal 250, something like that. We'll take a look to this information at the last slide, maybe in this article, in this lecture. The low curve, that's mean the blue one, shows difference between the experimental and calculated X-ray diffraction. Now, the green one explained to us the vertical bars. The vertical lines, the vertical bars indicate the position of Bragg's spakes. I take this information about definition about Bragg's spakes from Google. What does mean Bragg's spakes? The action of a crystal in the reflecting to X-ray or particle waves. The action of a crystal in reflection, X-ray or particle waves. Now, this table is very important. Explain to us what is happening to all of the diameter, the lattice parameters, the volume, the tolerance factor when increase the temperature from 900 until 1300. Actually, all of these results started from diameter and lattice parameter, volume, finish with tolerance. All of these are increased. Here, the result indicate the particle size in each sample are, here it's important, are several times bigger, larger than the crystalline size observed by, how I can say, SEM, scan electron microscopy method. It's a huge difference between the particle size and to this sample, or to in each sample, sorry, then it's a huge difference between the particle size here than the crystalline size observed by using scan electron microscopy method. Here, I was talked about it when increase the temperature from 900, the nanoparticle equal 120 nanometer. When increase the temperature to reach 900 Celsius. But when increase the temperature to reach 1300 instead of 900, the nanoparticle size equal 450. These small balls increase to be like that, from 120 to 450. Shows A and B, figure 4A and B shows the scan electron microscopy microbes for nanocrystalline samples S1, S2, like I explained before. Respectively, the average particle size increased from 120 to 450 nanometer. Here, to prove this line, the value of lattice accounts increased with crystallite size. Here, the lattice parameter increased when crystal size nanometer increased. Lattice constants or lattice parameters, some relation with the crystallite size. And at the same time, the unit cell volume sure increased when the lattice parameters increased, the volume sure will increase too. Here, the La0.7Sr0.3 manganese oxide has been synthesized successfully using nitrite glycine O2 composition method followed by calcination process to get different crystallite size. Here, I think it's the last one, the mixed valence peroviskite manganites at doping rate when X equal 0.3 shows the strongest manganese properties. Actually, in another article, something with Ca2+, I explained and I showed how the scientists prove by increase the doping rate, the stronger the manganese properties increased, and many things by using another table. We can take a look to this lecture from this channel. Yes, by increased the doping rate, a lot of things will increase, but until some amount, like when put the salt in water, at the first, this amount will disappear. That's depending on how much water we put in this glass. After that, when increased to some amount, the salt will stop to disappear. That's mean we will benefit from this phenomena, but until a specific amount. Let's note that. Now, the doping rate increase when by doping increase the doping rate, the magnetic properties will increase. Magnetic properties. That's it. Our lecture is done. Have a good time and thank you about your listening. Have a good day. Let me close it from here. That's it. Have a good day. See you in the next lecture.